In this video, we're going to talk about the difference between enantiomers and diastereomers. And this really becomes important when we have more than one chiral center in the molecule. So there are a number of different categories of isomers. Right? So the first types of isomers that we learned about were constitutional isomers. And so here we have the same number and type of each atom, but they're actually connected differently. Then we have stereoisomers, where they have the same connectivity, but different spatial orientations. And in general, stereoisomers are not superimposable on their other stereoisomers, even though they have the same connectivity. But even within stereoisomers, we have two different categories. We have enantiomers that we've talked about mostly so far, where the two compounds are mirror images of each other. So they're not superimposable, but they are mirror images. Diastereomers, not only are they not superimposable, but they're also not even mirror images. And as I said, we encounter diastereomers when we have more than one chiral center. So the cis and trans isomers that we first learned about in this chapter are examples of diastereomers. So we know they're stereoisomers, but they're also not mirror images of one another, and so they are diastereomers. And enantiomers have the same physical properties, although their chemical properties may be different when they're interacting with other chiral molecules. But diastereomers, not only do they have different chemical properties, they also have different physical properties. So here's an example of enantiomers and diastereomers. And as I've mentioned a couple times, right, the diastereomers occur when we have more than one chiral center. So if we consider our first molecule here, both of my chiral centers are R. And so to find its enantiomer, I have to swap both chiral centers out with the S. So this compound is the enantiomer of the first one. Right? And this compound has the same number and types of each atom, and it also has the same connectivity, but it's not the mirror image of the first compound. Right? To be the mirror image, I have to go from both R's to both being S's. Right? And in this case, this one went to S, but this one has stayed R. So they're stereoisomers, but they're not superimposable, and they're not mirror images. And so they would be classified as diastereomers. Now, when I compare these two, right, they are enantiomers, right, because this one has RS and this one has SR, so they both swapped. So these would also be enantiomers, right? And as far as the diastereomers go, right, these are also stereoisomers. They have the same connectivity, but they're not mirror images, and they're not the same compound. So these two would be diastereomers, and these two would also be diastereomers. And in general, the more chiral centers I have, the more diastereomers there are going to be. And so in this case, I have 3 chiral centers, and a compound, one of the compounds, right, in this case, the RRS, its enantiomer is SSR, and it will have always one enantiomer, and then all of the other stereoisomers that I can draw are going to be diastereomers of this one, or of this one, for that matter. And so when we have 3 chiral centers, I have 4 pairs of enantiomers. When I'm looking at this compound, if it's not its enantiomer, then all of these guys are its diastereomers. The analogy that the book likes to use is to consider a family, right? So in this family, they're all siblings. So we have 8 kids, they're all siblings, but each sibling, in the case of this unusual family, if there were 4 pairs of twins, right, we have 4 pairs of enantiomers. So these guys are enantiomers, but they're siblings of all these other ones. The total number of possible stereoisomers for a compound depends on the number of chirality centers, and the simple equation we have is the maximum number of stereoisomers is 2 to the n, where n is the number of chiral centers. And we say the maximum number. It turns out we may not have the full number of stereoisomers. Actually, we'll get into that in the next video when we talk about symmetry and compounds that are considered meso. But if we do one example, if I want to know the maximum number of possible cholesterol isomers, stereoisomers, we need to count the number of chiral centers. And so we have 1, 2, 3, 4, 5, 6, 7, 8. And so if I do 2 to the 8th, there are 256 possible stereoisomers. So there's this one. It will have 1 enantiomer, and then it will have 254 diastereomers. So let's take a look at a couple of examples on how questions might be framed related to this topic. And so one of the most common questions is to give us 2 compounds and ask whether they're enantiomers or diastereomers. And so remember, to be an enantiomer, all of the chiral centers have to switch to the opposite. So if it started at R, it has to become S. If it started at S, it has to become R. And all of them have to be opposite. In many instances, as long as the molecule is drawn in a helpful way, we don't even need to assign whether it's R and S. We just need to look, right, to draw the enantiomer of this guy. Anytime there's it's coming out towards us, I need to replace the wedge with the dash lines and replace the dash lines with the wedge. And so to draw the enantiomer of this, right, I turn this into the dashes, I turn this into the solids, right? And so this compound, right, the solid became the dash became the solid, so these are going to be enantiomers. All right, so similar compound, right? In order for these two to be enantiomers, right, we have to swap the solids with the dashes for everything. Right, and in this case, right, the solid becomes the dash, but the solids stay the solid. So that tells me that these are not enantiomers, and so they must be diastereomers. Okay, in this case, it wasn't drawn quite as helpfully, right? On the left-hand side, right, these two substituents are on the right. On the left-hand side, they're on the left. And so what I want to do is I want to redraw this molecule so I can compare these two. Right, but I have to redraw it in the proper way, and so I want to actually flip this guy 180 degrees, right? And so I'm essentially, if we imagine, putting a bar here, right, I'm going to flip it over. And so when I do that, all of the solids and dashes are going to swap with each other when I flip it over. So this becomes a dash. This becomes a solid, and that becomes a dash. And so now when I compare these two, right, they all have to switch. Okay, so the OH went from a solid to a dash, that's good, but this one went from a solid to a solid, right? So they're not enantiomers, so they must be diastereomers. Okay, here's another example, and in this case they've kind of messed us up, right? I can't even flip it to get to the same configurations, right? They've actually swapped these two groups, and so in this case, my only recourse is to assign the R and S configurations and then compare. And so if I'm going to be assigning priorities, right, I think this guy is actually easy, right? So on this one, on this chiral center, the solid should become a dash to be enantiomers, so I can see at least as far as this carbon is concerned, right, it's the opposite. So this is really the chiral center that I need to focus on. And so if I'm going to assign priorities, I think the priorities should be 1, 2, 3, right? But remember when I'm doing the R and S configurations, the hydrogen that's not shown should be in the back. So when I do these priorities, what I get is actually going to be the opposite of what this configuration actually is. And so these are going clockwise, but because this is going back, instead of the hydrogen, instead of being R, this is actually going to be S. And when I look at this one, for the priorities, I think again I'm going to have 1, 2, and 3. But again, this is going back instead of the hydrogen, so whatever I get is going to be backwards. So I would go 1, 2, 3, that's S. So it should be the opposite, so that's actually R. And so we can see, right, this chiral center flipped, and the S became the R, so these are enantiomers. Okay, here's another type of example where they want me to draw 2R, 3R, 2-bromo-3-chlorobutane. So both carbon atoms 2 and 3 are going to be chiral centers, and they both need to be R. So I'll start by drawing butane. Right, and then what I usually do, so I need to put in the bromine and the chlorine. So the bromine should go here, the chlorine should go here. What I usually do is just put them in as solid wedges, figure out what the which stereoisomer I have, and then swap it if it's wrong. So if I put in the solid wedge here for bromine, I think for the priorities I'm going to have 1, 2, 3. So I'm going clockwise, so having the wedge is correct. This is R. Do the same thing for the chlorine. Put it in as a solid wedge, see what I get. I think in this case my priorities are 1, 2, 3. And again, I'm going clockwise, so this is R. So this is the correct drawing of 2-bromo-3-chlorobutane. All right, another example. So here's the molecule that we drew last time. This is the 2-R3R, 2-bromo-3-chlorobutane, and now we want to draw the enantiomer. And so remember, when we want to draw the enantiomer, we just need to swap the solid wedges with dashes. And so if I turn both of those into dashes, then I'll have the 2S enantiomer. So this is going to be 2S3S, 2-bromo-3-chlorobutane. Okay, so now they want me to draw the 2 diastereomers of this compound. So this compound is RR, the enantiomer is SS, so the 2 diastereomers are going to be RS and SR. So if I draw, that would be R, S, and then this would be SR.